Good morning, student. I'm Dr. Dharmendra B N. This is my 7th session on elementary theory of partition. It's a unit 4 in theory of partition. Today we are discussing about the representation of an integer as a sum of two squares. Very important. And also that's a representation of integer as a sum of 4 square. And one more theorem with that example. These two theorems are very important. There is a representation of an integer as a sum of 2 square and the representation of integer as a sum of 4 square. Okay. So just we have to go through this first one. What is that representation of integer as a sum of 2 square? That means when I have to take n is equal to 1, that can be written as in terms of a square sum of 2 squares, that is a square plus b square, and that representation can be written as in terms of r suffix 2 of n. Just we have to take that table, that is a n, it's a integer, it's a positive integer, that is a square plus b square, that can be written as and r2 of n. How many times we have to write the terms of the sum of two squares? Okay. Suppose when I have to choose n is equal to 1, we can observe that it can be written as in terms of a sum of two squares. So 1 can be written as, that is a sum of two square is, we can easily predict, that is a 0 square plus 1 square. Okay. Next, when I have to interchange the terms of here, replace 1 by minus 1, again that becomes 1, that is 0 square plus minus 1 square, that is the another representation. Okay, a representation of 1, the second representation of 1 as 0 square plus minus 1 square. The another one is when I have to interchange that values, that is 1 square plus 0 square. Okay, and the next one we have to replace the value of 1 by minus 1 square plus 0 square. So therefore the sum becomes 1. So therefore it can be written as the fourth representation of 1, that is a minus 1 square plus 0 square. So overall the terms is the representation of an integer as a sum of 2 square, that is the representation of a 1 as a sum of 2 square is 4, that is 0 square plus 1 square, 0 square plus minus 1 square, 1 square plus 0 square, and the last one is minus 1 square plus 0 square, that is equal to 4. That is the representation of 1 as a sum of 2 square is 4. Okay. Similarly, when I have to take the next one, suppose 2, that number 2 can be written as the terms is 1 square plus 1 square. So 1 square plus 1 square means that is 1 plus 1, that is equal to 2. Again, now to take the second one, we should replace the value of 1 by minus 1. It can be written as the terms is 1 square plus minus 1 square, that is also 1 plus 1, that is 2. Again, when I have to replace that last one, the here first term, 1 replace 1 by minus 1, that is minus 1 square plus 1 square, that is also is equal to 2. Again, suppose we have to take the both are negative, that is 1 minus 1 square plus minus 1 square, that is also is equal to 2. So overall that there are 4 representation, the representation of 2 as a sum of 2 squares, that is the representation of n means the representation of 2 is 1 square plus 1 square, 1 square plus minus 1 square, minus 1 square plus 1 square, minus 1 square plus minus 1 square. Overall the terms is that is 4. The representation of 2 as a sum of 2 square is 4. Similarly, when I have to choose that next one is suppose 3 couldn't write the terms of in terms of a sum of 2 squares, because 0 square plus 3 square, okay, again the terms is you can write that that means that is 0 plus 9, or we have to write in terms of 1 square plus 2 square, that is 1 square plus 4 square, 2 square, that becomes 5. So that's why we couldn't write the terms of that example. So that's why I take next one is a 5. Again similarly in terms of 4 can be written as 2 square plus 2 square, that is also that is a representation. 2 square plus 2 square is 4 plus 4, that is 8. That we couldn't write the terms as easily. So that's why I can take that next one is a 5. 5 can be written as that is 1 square plus 2 square. It can be rewritten as the terms of 1 square plus minus 2 square. Again, next representation of 5 as a sum of 2 square, that is a minus 1 square plus 2 square. Both are negative, the terms is that is minus 1 square plus minus 2 square. Again, we have to rearrange the terms of 1 square plus 2 square can be written as 2 square plus 1 square. Again, next one is we have to change that at least any one of the terms is a negative term, that is a 2 square plus minus 1 square. Again, next one minus 2 square plus 1 square. Again, the both are negative, minus 2 square plus minus 1 square. Overall, there is a 5. The representation of 5 as a sum of 2 square is 8. 1 square plus 2 square, 1 square minus 2 square up to minus 2 square plus minus 1 square. So, overall the terms is 8. Similarly, the next number is 8, that is a 2 square plus 2 square, that is a 4 plus 4, that is 8. Or also can be written as, at least we have to take any one of the terms is a negative, that is a 2 square plus minus 2 square. The next one is minus 2 square plus 2 square. Both are negative. The next number is minus 2 square plus minus 2 square. For all the terms of the representation of 8 as a sum of 4 square is 4 times. Okay. Again, similarly, in terms of 10, the next number, that is a 1 square plus 3 square, that is a 1 plus 9, that is equal to 10. Again, here also we have to take that number is 1 square, at least any one of the terms is negative, that is 1 square plus minus 3 square. Next number is minus 1 square plus 3 square. The next number is both are negative, minus 1 square plus minus 3 square. So, I have to interchange these two numbers, that is 3 square plus 1 square. Then next one is at least any one of that number is negative, that is 3 square minus 1 square. The next number is minus 3 square plus 1 square. Then both are negative, minus 3 square plus minus 1 square. That is overall the terms is the representation of 10 as a sum of 2 square, that is 8 times. That is, you can observe the term. And the next one, that is 18. So, the next number is 18, that is a 3 square plus 3 square, that is 9 plus 9, that is 18. At least any one of that number is negative, that is 3 square plus minus 3 square, or minus 3 square plus 3 square, or both are negative, minus 3 square plus minus 3 square. That is overall the representation is for 18. The representation of 18 as a sum of 4 square is 4 type. That is 3 square plus 3 square, 3 square minus 3 square, minus 3 square plus 3 square, minus 3 square plus minus 3 square, that is equal to 4 times. That's okay. We have to prove this one by mathematically in the theorem. Let r suffix 2 of n, r suffix 2 of n, that represent the representation of an integer as a sum of 2 square, as a sum of 2 square, that is let r suffix 2 of n denotes the number of representation of n as a sum of 4 square k square. That the terms of k means that is k is equal to 2 here. Okay, and d suffix I comma j, you can observe terms of d suffix I comma j of n denotes the number of positive divisors that are congruent to I modulo j. Okay, suppose when I have to consider that number is n, the divisors of n is congruent to 1 modulo I modulo j. That representation of d suffix I comma j is the number of positive divisors of n. Okay, the positive divisors of n that are congruent to I modulo j. I means that is that remainder, that is modulo j. Okay, then the representation of 2 of n is equal to 4 times d suffix 1 comma 4 of n minus d suffix 3 comma 4 of n. That means the divisors of n which are congruent to 1 modulo 4, and this one is the divisors of n which that is congruent to 3 modulo 4. So, R2 of n is equal to 4 times the divisors of n which are congruent to 1 modulo 4 minus divisors of n which are congruent to 3 modulo 4. So, this one we have to by using the terms of the theorem, that is summation n running from minus infinity to plus infinity a n by b n into z to the power of n. The terms can be written as, that is a z infinity into q by a z infinity into b by a infinity q infinity divided by z infinity into b by a z infinity into q by a infinity into b infinity. The condition is b by a is less than mod q is less than 1, and also with the terms of mod q is less than 1. In this formula, we have to put b is equal to a q. We have to put in the above the values. You can replace the terms of b by a q. So therefore, summation n running from minus infinity to plus infinity, a n divided by, when you have to replace b by a q, that is a q n into z to the power of n, that is equal to, that is there is in the numerator, that is a z infinity q by a z infinity, there is nothing change, but the terms of the third term, when you have to replace b by a q, that is a q by a, that is a get cancelled, so the terms is only q infinity, here also q infinity divided by here z infinity into b. We have to replace b by a q, that is a get cancelled, that is q by z infinity, here q by a infinity and the terms of a q infinity, that is the term here. Okay, here a get cancelled in the third term, that is only in terms of q infinity. Here the terms is a get cancelled, that is a q by z infinity. So therefore, and also when I have to expand the terms of by q shifted factorial, a n can be written as, that is a n means that is a q n. Here in the denominator, that is a q q n. The first term is a 1 minus a, and the next term is 1 minus a q, the last term is 1 minus a q to the power of n minus 1. Here the first term is 1 minus a q, the next term is 1 minus a q square, and the last term is 1 minus a q to the power of n. You can expand that by using q shifted factorial, that is equal to, you can observe the terms is summation ending from minus infinity to plus infinity, 1 minus a, 1 minus a q, 1 minus a q to the power of n minus 1. Here the denominator term is 1 minus a q into 1 minus a q square up to 1 minus a q to the power of n into z to the power of m. Here the terms is in the numerator except the first term. Okay, the remaining term is cancelled with the denominator term is 1 minus a q to the power of n, 1 q to the power of 2 up to the terms containing 1 minus a q to the power of n minus 1. So we are to leaving the terms of in the left hand side, that is 1 minus a divided by 1 minus a q to the power of n into z to the power of n, that is equal to a q infinity, a z infinity q by a z infinity q q infinity into q q infinity divided by z infinity into q by z infinity q by a infinity into a q infinity. So here we have to cancel the terms. The remaining term is summation n running from minus infinity to plus infinity, 1 minus a divided by 1 minus a q to the power of n into z to the power of n. That is equal to here q infinity, that becomes q infinity whole square, that is a z infinity q by a z infinity into q infinity whole square divided by z infinity into q by z infinity q by a infinity a q infinity. When I have to put a is equal to minus 1 in the above equation, that becomes minus 1 means there is 1 minus of minus 1, that becomes 2. Here 1 plus q to the power of m. The remaining term here a is equal to minus 1 means that is a minus infinity, minus z infinity. Here the terms is minus q by z infinity and q infinity whole square divided by z infinity q by z infinity minus q infinity, here also minus q infinity, because a is equal to minus 1. So, with that expansion of the terms of q, that can be representation of the above equation is, that is the numerator term becomes 1 plus 1, that becomes 2. We have to put a is equal to minus 1. So, summation entering from minus n to plus infinity divided by 1 plus q to the power of n into z to the power of n is equal to, we can express with the terms of q, that is here minus q, minus z q infinity into minus q by z q infinity into q infinity whole square divided by z infinity into q by z q infinity minus q infinity minus q infinity. So, this term becomes minus q infinity whole square. When I have to replace in the above equation, replace q by q square. In this equation, we can replace q by q square. We get the terms is summation from minus infinity plus infinity 2 divided by 1 plus q square whole to the power of n into z to the power of n, because we have to replace q by q square. That is equal to, on the right hand side, that is a minus z q square infinity minus q square z q square infinity q square infinity whole square, and the terms is denominator divided by z q square infinity q square by z q square infinity minus q square infinity whole square, because this term is twice, that's why I can take the square. And then we can replace the terms of in the above equation, we can replace the z by q. Okay, you can replace z by q, it becomes summation entering from minus infinity plus infinity 2 divided by 1 plus q square whole to the power of n into q to the power of n is equal to, that is minus q square infinity. Here the terms is when I have to put z by q, that is q square by q, that is minus q square infinity, here q square infinity whole square, and the terms here also the terms is q square infinity, here also q square by q means that is a q square infinity into minus q square infinity whole square. So, therefore, here we have to observe the terms as the two terms minus q square infinity minus q square infinity, that becomes square. Here also q square infinity, here also q square infinity. So, therefore, q infinity, q square infinity whole square. So, therefore, and also we can split that LHS side as a negative integer, positive integer, and the terms of n is equal to 0. So, we have to split into 3 parts. The first one is a negative integer and n is equal to 0 and n is a positive integer. So, therefore, we can take 2 as a constant and we can take it outside, that is 2 times summation and from minus infinity to minus 1 to the power of n divided by 1 plus q to the power of 2n plus 1 by 2 times, because when I have to take n is equal to 0, that becomes q to the power of 0, and this one is also q to the power of 0 is 1. The denominator term is 1 plus q square whole to the power of 0. You know the value of q, anything to the power of 0 except infinity, the terms is it becomes 1, that is 1 plus 1, that is 2. So, there is n is equal to 0 and n is a positive integer, is n varies from 1 to infinity q to the power of n divided by 1 plus q to the power of 2n. That is equal to, here that square terms, that is equals minus q square infinity whole square into q square infinity whole square divided by q square infinity whole square into minus q square infinity whole square. So, we have to observe that the right hand side, this all are whole square, we can observe terms of, and also we have to, in the left hand side, in the first series we can replace n by minus n. So, therefore, the series becomes varies from positive integer. When I have to replace n by minus n, so that is q to the power of minus n divided by 1 plus q to the power of q to the power of minus 2n. We can take minus 2n as a common factor, that becomes q to the power 1 plus q to the power of 2n, it will go to numerator, that's q to the power of minus n plus 2n. So, therefore, that becomes q to the power of n divided by 1 plus q to the power of 2n. So, when after the replacement of n by minus n in the first series, it can be rewritten as 2 times summation n running from 1 to infinity q to the power of n minus n divided by 1 plus q to the power of minus 2n. In this series, we can take in the denominator, we can take q to the power of minus 2n as a common term, that becomes q to the power of 2n plus 1, or it will goes to numerator, that is q to the power of plus 2n into q to the power of minus n. So that becomes q to the power of minus n plus 2n, that becomes q to the power of n. This is same as the remaining term is 1 plus 2n, 1 by 2 plus summation from 1 to infinity q to the power of n divided by q to the power 1 plus q to the power of 2n is equal to the right hand side. It is that is not containing square here. It's not the terms of 2, because already we have to take in square root. This is a typing error. So minus q square infinity into q square infinity divided by q square infinity minus q square infinity whole square. Overall the terms of is not containing a square term, so it's a typing error, and we have to multiply and divided by q to the power of 2n in the this term, that becomes the first series, that becomes q to the power of n divided by 1 plus q to the power of 2n, that is a 2 times summation from 1 to infinity q to the power of n divided by 1 plus q to the power of 2n plus 1 by 2 plus summation n from 1 to infinity q to the power of n by 1 plus q to the power of 2n, and the remaining term, that is equal to what we have to take in terms of a square. The square terms becomes, that is the definition of phi of q. What is phi of q? The definition is, that is the terms here, minus q square infinity q square infinity divided by q square infinity minus q square infinity. That is nothing but the definition of phi of q whole square. Or we have to multiply the terms of inside 2, that becomes, and also there are the 2 terms here, there, it is a 2 times summation n from 1 to infinity q to the power of n divided by 1 plus q to the power of 2n plus to multiply the 2 by 2, that becomes 1 plus 2 times summation n from 1 to infinity q to the power of n divided by 1 plus q to the power of 2n is equal to your phi square of q. Okay, or here 2 times is there, that becomes 1 plus 4 times q to the n summation n from 1 to infinity q to the power of n divided by 1 plus q to the power of 2n is equal to phi square of q, or phi square of q is equal to 1 plus 4 times summation n from 1 to infinity q to the power of n divided by 1 plus q to the power of 2n, or it can be rewritten as the terms is phi square of q is equal to 1 plus 4 into summation n from 1 to infinity q to the power of n into 1 divided by 1 plus q to the power of 2n. So this is the representation of 1 divided by 1 plus x. If x is less than 1, that can be written as the terms is 1 plus x square up to the terms of infinite. So it can be written as, by using the concept, 1 by 1 plus q can be written as 1 minus q plus q square minus q plus, that is alternative signs. The terms can be written as, that is summation m running from 0 to infinity minus 1 to the power of m into q to the power of m. Here instead of that value of 1 divided by q to the power of 1 divided by q to the power of 1, here 1 divided by 1 plus q to the power of 2n. We can observe the terms here, q to the power of 2n is there, here q is there. So what we have to replace? We should replace q by q to the power of 2n. That becomes summation n running from 0 to infinity minus 1 to the power of m into q to the power of 2n whole to the power of m. In the next step, we can replace this whole term, that is the value of 1 divided by 1 plus q to the power of 2n can be written as summation m running from 0 to infinity minus 1 to the power of m into q to the power of 2n whole to the power of m, because we have to replace the value of q by q to the power of 2n. So therefore phi square of q is equal to 1 plus 4 times summation n running from 1 to infinity q to the power of n into summation m running from 0 to infinity minus 1 to the power of m into q to the power of 2n whole to the power of m. So therefore, or it can be rewritten as the terms is q q to the power of 2n whole to the power of m can be written as q to the power of 2mn. The next step, phi square of q is equal to 1 plus 4 times summation n running from 1 to infinity q to the power of n into summation m running from 0 to infinity minus 1 to the power of m into q to the power of 2mn. So we have to multiply the terms of here q to the power of n. You can observe the terms, or we can split into even and odd term of m here. Terms here, we can replace the terms of phi square of q can be written as phi of q into phi of q, and also the terms of m running from 0 to infinity. Okay, if m running from 0 to infinity, one have to consider if m is a even, that becomes this term becomes we can replace minus 1 to the power of 2m. If m becomes odd, that is 2m minus 1, that becomes negative, that is we can replace the value of m by 2m plus 1 or 2m minus 1. The terms is here 2m plus 1. We can split m as even and odd term. If m is a even, this term becomes positive. If m is a odd, this term becomes negative. So, and also the terms of phi square of q can be written as phi of q into phi of q. We know the statement of phi of q in terms of a series, that is minus infinity to plus infinity q to the power of n square. So, instead of the terms, it can be written as summation k running from k suffix 1 is equal to minus infinity to plus infinity q to the power of k1 square into summation running from k2 is equal to minus infinity to plus infinity q to the power of k2 square, because phi of q into phi of q can be written as in terms of a series, that is the first series is k1 running from minus infinity to plus infinity q to the power of k1 square. The second one, that's phi of q, that is summation k2 running from minus infinity to plus infinity q to the power of k2 square, that is equal to 1 plus 4 times summation n running from 1 to infinity q to the power of n into, if m is a even, the terms can be written as m running from 0 to infinity q to the power of m is even means that is 2m, that is 2, already 2 is there, that is 2 into 2m into n, that is a 4m q to the power of 4mn. Again, if m is odd, that becomes 2m plus 1, that is minus the text that negative sign, that is m running from 0 to infinity q to the power of 4m, because 2 is one have to multiply the terms of 2m plus 1, and if you replace m by 2m n, 2m plus 1, that becomes 2m plus 2 into n. And also we have to multiply inside the terms of q to the power of n, and we have to take the series s in terms of the two series. The first series running from minus infinity to plus infinity, here missing the terms of infinity. Here also k2 running from minus infinity to plus infinity, here missing the terms of infinity, the typing error. Here infinity is there in both the series. Q running k to the power of k1 square plus k2 square, that is equal to 1 plus 4 times summation n running from 1 to infinity, that is we have to multiply the terms of q to the power of n inside the series, that is m running from 0 to infinity q to the power of 4m plus 4mn plus n minus summation m running from 0 to infinity 4mn plus 2n plus n. So therefore, it can be rewritten as the series is k1 running from minus infinity to plus infinity, k2 running from minus infinity to plus infinity, k1 square plus k2 square is equal to here that is equal to 1 plus 4 times summation n running from 1 to infinity summation q to the power of summation m running from 0 to infinity q to the power of, you can take n as a common term here, that is n into 4m plus 1 minus summation m running from 0 to infinity q to the power of n into 4m plus 3, because 2m n plus m, that becomes 3m. You can take it n as a common factor, that is 4m plus 3. So this is the representation is, let's say You can observe that series here. That representation is that is a representation of an integer, that is a divisors of an integer which are congruent to 1 modulo 4. That is the first series. The second series also, that is the representation of n, that is a divisors of n which are congruent to 3 modulo 4. Okay, these two representation. So therefore it can be written as summation k1 running from minus infinity to plus infinity. That is first series. The second series is k2 running from minus infinity to plus infinity q to the power of k1 square plus k2 square, that is equal to 1 plus 4 times summation n running from 1 to infinity. The first series indicates the terms of 4n plus 1 means that is a divisors of n which are congruent to 1 modulo 4 minus divisors of n which is congruent to 3 modulo 4, that is 4m plus 3 into q to the power of n. Then the comparing the coefficients of n, the terms is suppose if k1 square plus k2 square is equal to n, both the first series running from minus infinity to plus infinity, so the second one is also minus infinity to plus infinity q to the power of n, where n is k1 square plus k2 square, that is equal to 1 plus 4 times summation n running from 1 to infinity d suffix 1 comma 4 of n minus d suffix 3 comma 4 of n into q to the power of n. So when after equating the coefficient of n, if n is greater than or equal to 1, that is the both the case, so therefore we get that is a r suffix 2, that is n means that is a representation of n is a sum of two squares, that is r2 of n, r2 of n is equal to 4 times what is the coefficient of q to the power of n on the RHS side, that is d suffix 1 comma 4 of n minus d suffix 3 comma 4 of n. So by using the Ramanujan's 1/1 summation, we can deduce the this representation, that is the representation of n as a sum of k square, here the sum of 2 square and d suffix I comma j, that is that d suffix I comma j is denotes the number of positive divisors of n that are congruent to I mod j, then r suffix 2 of n is equal to 4 times d suffix 1 comma 4 of n minus d suffix 3 comma 4 of n. So this is very important, and also we have to verify by using the table. We have to note down the terms. How can we find out the value of this one? We have to take that LHS side is, that is a phi square of q. We know the value of phi square of q is phi of q into phi of q. What is phi of q into phi of q? By using that in terms of a series, that is the first series is summation n1 running from minus infinity to plus infinity, not here also typing error, that is minus infinity to plus infinity q to the power of n1 square into summation n2, this is not n1, that is n2 running from minus infinity to plus infinity q to the power of n2 square. Okay, this one is n1 running from minus infinity to plus infinity, not infinity, that is minus infinity to plus infinity q to the power of n1 square into the second one phi of q is n2, not n1, that is n2 is running from minus infinity to plus infinity q to the power of n2 square. So when I have to expand the terms of the first series, that can be written as that is n is equal to 0, n is equal to 1, n is equal to minus 1, n1 is equal to 2, n1 is equal to minus 2. We can observe here the terms is n is equal to 0, that is q to the power of 0 whole square. Again, if n is equal to 1, that is q to the power, n1 is equal to 1, that is q to the power of 1 square, n1 is equal to 2, that is q to the power of 2 square. Again, q to the power of minus 1 square, again q to the power of minus 2 whole square up to infinite term. Similar in terms of the second one into summation, here also q to the power of 0 whole square, that is n1, n2 is equal to 0, n2 is equal to 1, that is q to the power of 1 square, n2 is equal to 2, that is q to the power of 2 square, Again, we have to take negative integers, that is q to the power of minus 1 square, that is n2 is equal to minus 1, and n2 is equal to minus 2, that is q to the power of minus 2 whole square. So, up to infinitum. Now, we can take in the representation of 2. We have to multiply the terms of the representation of 2 here, and also the representation of 1 and 2. So, that is R2 of 1. We can observe the terms is when you have to taking a q to the power of 0 whole square, we have to observe here we can multiply the terms of q to the power of 0 whole square, that is a representation of 1 as a sum of 2 square. You can multiply q to the power of 0 square into q to the power of 0 square, because there is a multiplication is here, q to the power of 0 square into q to the power of 1 square, that becomes q to the power of 0 square plus 1 square, that is a representation of 1 as a sum of 2 square. Similarly, here q to the power of 0 square into q to the power of minus 1 square. Okay. Similarly, here another one is q to the power of 0 square is there, that is also q to the power of 0 square into q to the power of minus 1 square. Here also q to the power of 0 square is q to the power of 1 square. So, overall the terms is 4 times. So, we can observe here the terms is that is a representation of 1 as a sum of 2 square, that is 4 into q. You can observe terms of 0 square means that is 0. Again 1 square is that is 1. So, that is q to the power of 1. Okay, that is a representation of 1 as a sum of 4 square, that is equal to 4, that is you can observe here 4 into q. It is q to the power of 0 square plus 1 square, q to the power of 0 square to minus 1 square, again q to the power of 1 square, you can observe terms of plus 0 square, q to the power of minus 1 square to q to the power of 0 square. So, overall that is a representation of 1 as a sum of 2 square is 4, that is R2 of 1 is equal to 4, that is 4 into q. Similarly, suppose n is equal to 2, okay, n is equal to 2, that can be written as q to the power of 1 square plus 1 square. You can observe here q to the power of 1 square into q to the power of 1 square, okay. Again q to the power of 1 square into q to the power of minus 1 square, okay. That is minus 1 square means that is 1, so that is equal to 2. So, similarly in terms of here q to the power of minus 1 square into q to the power of 1 square, again with the terms of q to the power of minus 1 square into q to the power of minus 1 square, overall that is representation is 4. This one is, you can observe the terms, that is 4 times q to the power of q square, that is R2 of 2 is equal to 4. So, this is the representation, and also we have to we have to verify that previous theorem, that is R suffix 2 of n is equal to 4 times d suffix. What is d? Is the divisors of n which are congruent to 1 modulo 4 minus divisors of n which are congruent to 3 modulo 4. You can observe the table here. If n is equal to 1, this R2 of n means that is a representation of an integer as a sum of 2 square, and these divisors of n, what is the divisors of n? And divisors of n which are congruent to 1 modulo 4, that is divisors of n which is congruent to 3 modulo 4, and the terms of it is a 4 times divisors of 1 comma 4 minus divisors of 3 comma 4 of n. So, therefore, what is n is equal to 1, what is the representation of 1 as a sum of 2 square, that is 4, and the divisors of n is only 1, and which are congruent to the divisors of n which is congruent to 1 modulo 4, that is 1, because this already is congruent to 1 modulo 4. Again, if it is a 3 modulo 4, divisors of n, that is 0. So, therefore, 4 into, what is that number here? 1 minus 1, that is 4 into 1 is equal to 4. So, therefore, both are same. That is 4 is equal to 4. That means R2 of n is equal to 4 times d suffix 1 comma 4 of n minus d suffix 3 comma 4 of n. So similarly, when I have to check d is equal n is equal to 2, what is the representation of 2 as a sum of 4 square, that is 4, and divisors of n is the divisors of 2 is 1 and 2, and the divisors of n which are congruent to 1 modulo 4 is, that is 1. So that is the divisors of 3 comma 4, divisors of n which are congruent to 3 modulo 4, that is 0. So therefore 4 into 1 minus 0, that is also is equal to 4. So therefore the theorem is holds good. R suffix 2 of 2 is equal to 4 times d suffix 1 comma 4 minus d suffix 3 comma 4. Similarly, I have to take 3, that is the representation of 3 as a sum of 2 square, that is equal to 0. So we couldn't write in terms of a square sum of 2 squares. So what are the divisors of n? The divisors of n are 1 and 3. So therefore the divisors of 1 comma 4, definitely that is containing 1 is there. Again 3 is also there, that is congruent to 3 modulo 4. So therefore that is a 4 into 1 minus 1, that is equal to 0. So therefore this one is also holds good. Similarly, the remaining term you can try yourself. Definitely that must be holds good for all the values of up to the terms of 4, 5, 6, n is equal to 7 and 8. You can observe the terms. Next we can move on to the representation of an integer as a sum of 4 square. As a sum of 4 square means that is a square plus b square plus c square plus d square. Suppose n is a the representation of a positive integer, that is n can be written as a sum of 4 square, that is a square plus b square plus c square plus d square. So therefore n, that is that value of m, and the divisors of n, and the terms is here we have to observe the terms of n. Divisors of n is 1, again divisors of n, but 4 does not divide d. Camber terms of 4 does not divide d, that is also 1, and a is equal to 1. A is that representation of, that is 4, the representation of 4 of n, that is 8 into a. You can observe the terms of what is the representation of 4 of n. That means the representation of 1 in terms of 4 squares, that is 1 square plus 0 square plus 0 square plus 1 square, again 0 square plus 1 square plus 0 square plus 0 square, again 0 square plus 0 square plus 1 square plus 0 square, and lastly the terms of 0 square plus 0 square plus 0 square plus 1 square. In above that all these values we can replace 1 by minus 1. So therefore we can observe the terms of minus 1 square, 0 square plus 0 square plus 0 square, and 0 square minus 1 square plus 0 square plus 0 square, 0 square plus 0 square plus minus 1 square plus 0 square, lastly the terms of 0 square plus 0 square plus 0 square plus minus 1 square. So that is the representation of 1 as a sum of 4 square is, that is 8 times. You can observe terms of. Similarly, in terms of if n is equal to 2, the divisors of n, that is the divisors of 1, 2 are 1 and 2, and divisors of n, and the terms of, that is 4 does not divide d, it's 1 comma 2, and a is the representation of r suffix 4 of n, the terms is 8 into a, that is 24. So we can observe here. So there are 24 times r suffix 4 of n. Okay. So it should be continued in terms of 1 square plus 1 square plus 0 square plus 0 square, 1 square plus 0 square plus 1 square plus 0 square, again 1 square plus 0 square, 0 square plus 1 square, again 0 square plus 1 square plus 1 square plus 0 square, again 0 square plus 0 square plus 1 square plus 0 square. So overall the terms is 1, 2, 3, 4, 5. So we have to take the at least one is a negative term. We can write all those things. Again, next one is a negative term, and we can write down all those things. And both are negative terms, we can write them. So overall, the 6 into 4 times the terms is 24 times. Okay. So the representation of 2 as a sum of 4 square, that can be written as in terms of 24 times. Okay. Similarly, we can check the terms of 3, 4, 5, 6, 7 and 8. The terms is okay. Next one is Jacobi 4 square theorem. The representation is Jacobi 4 square theorem. So we can observe that value. Where what is the value of the last one? It is A means that is a summation d divides n, but the d does not divides d. Okay. If n is a positive integer, the theorem statement Jacobi 4 square theorem. If n is a positive integer, then r suffix 4 of n is equal to 8 times summation d divides n, but d does not 4 does not divides d. We are missing the terms of 4 does not divides d. This d, where r suffix 4 of n stands the number of representation of n as a sum of 4 square. Okay, as a sum of 4 square. We know that is a phi of q, that is in terms of a series. Phi of q is equal to summation n running from minus infinity to plus infinity q to the power of n square. When I have to take in that 4 times, that is phi to the power of 4 of q is equal to phi of q into phi of q into phi of q into phi of q 4 times. We can replace the value of that is n by k1, k1, k2, k3, k4. Therefore, phi 4 phi to the power of 4 of q is equal to k1. The first one, phi of q is k1 summation k1 is varies from minus infinity to plus infinity q to the power of k1 square into the second phi of q is summation k2 running from minus infinity to plus infinity q to the power of k2 square, and the next one summation k3 running from minus infinity to plus infinity q to the power of k3 square. The last one of phi of q is summation running from k4 is equal to minus infinity plus infinity q to the power of k4 whole square. So therefore, phi to the power of 4 of q is equal to that fourth series, that is for the first one the first one series is k1 running from minus infinity to plus infinity, the second one series is minus infinity to plus infinity, the third one k3 is varies from minus infinity to plus infinity, the fourth series varies from k4 running from minus infinity to plus infinity. So that is q to the power of k1 square plus k2 square plus k3 square plus k to the power of 4 square. Or it can be rewritten as the terms of when I have to take k is equal to 0, we have to observe terms of all the values of k1, k2, k3, k4, all the values from 0. The remaining terms, that is phi to the power of 4 of q is equal to 1 plus, that is the terms of n running from 0 to infinity r suffix 4 of n into q to the power of n, where n running from k1 square plus k2 square plus k3 square plus k4 square, all these values must be greater than or equal to 1. So this one proved by the terms of by using Belli's transformation formula. The sums of two squares we have to prove by the terms of Ramanujan one summation formula. So here to take in terms of Bailey's transformation formula, we know that the Bailey's transformation formula is summation n running from minus infinity to plus infinity a n bn divided by cn into dn into z to the power of n. What is the value of a n? Means that is a by q shifted factorial, that is a q n. The base is q is there. Here also b is also b q n divided by c q n and the terms of dqm into z to the power of n, that is equal to, that is we have to write simply, that is az infinity, again the terms of d by a infinity, c by b infinity, dq by ab z infinity divided by z infinity into d infinity into b by q by b infinity into cd divided by abz infinity into summation n running from minus infinity to plus infinity an into abz by dn divided by azn into cn into d by a whole to the power of n. So we have to remember this one, that is a Bayes transformation formula, and also one have to put b is equal to a and d is equal to c. You can observe terms of in this Bayes transformation formula, we can put b is equal to a and d is equal to c. So that can be written as b is equal to a and d is equal to c, means that is a an into an divided by cn into cn, that becomes an square divided by cn square. The remaining term, the terms is here b by a, and here also terms of in terms of c by a, and the terms is this one is c by a. Okay, here d can replace d by c, that is a c q divided by, that is a b by a, means that is a square z infinity divided by z infinity, here c infinity into q by a infinity into, that is cd, means that is the terms of d is c, that is a c square divided by a square z infinity into summation n running from minus infinity plus infinity an into, when after the replacement of b by a and c by d, the terms is here a square z by cn divided by a zn and cn into, the terms is c by a whole to the power of n. You can observe that values after the replacement of b by a and d by c, that is summation n from minus infinity to plus infinity an whole square divided by cn whole square, because b is equal to a and d is equal to c, that left hand side. The right hand side, that is equal to summation az infinity into c by a infinity into c by a infinity into cq divided by a square z infinity divided by z infinity into c infinity into q by a infinity into c square by a square z infinity into summation n from minus infinity to plus infinity an into a square z by cn divided by az into cn into c by a whole to the power of n. Here the terms containing c by a infinity or c by a infinity, that becomes c by a infinity whole square. So therefore, and also we have to put in this value, that is a is equal to minus 1, c is equal to minus q and z is equal to minus q. You can observe terms of a is equal to minus 1, c is equal to minus q and z is equal to minus q. A is equal to minus 1, c is equal to minus q and z is also is equal to minus q. We have to observe the terms here, that is minus 1 whole square and minus q infinity n whole square and minus q to the power of m. The remaining term, a is equal to minus 1 and c is equal to minus q, that is minus q the terms of q infinity, because minus q by minus 1, that is q. Here also minus q by minus 1, that is q. This one is minus z infinity q infinity, this becomes q square, because the terms of minus q square divided by z, that is the terms of here also q, that becomes, this one is also q infinity divided by the terms of z is minus q infinity and c is also minus q infinity, a is that this one is also minus q infinity into, that is q square, and the terms of this one is also q infinity. And when I have to replace the value of a is minus 1 and c is equal to minus q and z is equal to minus q, these two terms get cancelled at the terms and divided by here the terms of q, because minus 1 minus z minus q and minus 1, that becomes qn, and this one is minus qn into c, means that is minus q by minus 1, that becomes q to the power of n. So therefore, After the replacement of a is equal to minus 1, b is equal to c is equal to minus q and z is equal to minus q, that can be written as the left hand side, that is running from minus infinity to plus infinity, minus 1 q n whole square divided by minus q n whole square into minus q to the power of n. The numerator term, the whole terms becomes q infinity, that is 4 times, and the denominator is also minus q infinity, so that is 4 times into summation n running from minus infinity to plus infinity. We can observe the terms here. Summation n running from 1 to infinity is a minus 1 qn into 1 qn divided by qn into minus qn into q to the power of n. This whole term becomes 1 because the terms containing here 1 qn. We know the value of the expansion of q shifted factorial. If the terms containing 1 is there, that is 1 minus 1, that becomes 0. You can observe terms of 1 minus 1, that becomes 0 because 1 minus 1, 1 minus q, 1 minus q square. The expansion of these terms, that becomes 0 because the terms n varies from minus infinity to plus infinity. So except the terms of the values of we can split that values can be written as in terms of n is a positive integer, negative integer, and n is equal to 0. So except the first two terms, n is a positive integer, n is a negative integer, both that values are 0 because 1 q n is there, okay, and the remaining terms n is equal to 0, that value becomes 1 because we know the value of that q shifted factorial. If n is equal to 0, that value is equal to 1 because n is equal to 0 means all these values are 0 0 and q to the power of 0, that is also 1. So therefore this value become the entire series, that value becomes 1 because the terms containing 1 q n is there. The expansion of 1 q n by using q shifted factorial, that becomes 0 except that except the terms of n is equal to 0. The terms of, so the remaining term is also except a value of n is equal to 0. If n is equal to 0, that value becomes 1. So otherwise a positive integer, that is 1 q n, that is also 0, 1 q minus n, that is also 0. So therefore, and also we can expand that numerator and denominator terms of minus q square n divided by minus 1 q n whole square divided by minus q n whole square. So by using q shifted factorial, that can be written as summation n from minus infinity to plus infinity. This one is negative term is there, that is 1 plus 1 whole square, 1 plus q whole square, 1 plus q square whole square, up to terms of 1 plus q to the power of minus n whole square divided by the terms is 1 plus q whole square, 1 plus q square whole square, up to the terms containing 1 plus q to the power of n minus 1 whole square into 1 plus q to the qn whole square. Here except the first term, the remaining term cancel with the denominator. We can observe here 1 plus q square up to 1 plus q to the power of n minus 1 whole square. Here also the terms is 1 plus q whole square up to 1 plus q to the power of n minus 1 whole square. Okay, these two get cancelled. On the right hand side, that is the terms is q infinity whole to the power of 4 minus q infinity whole to the power of 4 into 1, because 1 q infinity, that becomes 0. We have to split that this series as a positive integer, negative integer, and n is equal to 0. If n is equal to 0, that is equal to 1, that is this value. The remaining terms, that value becomes 0, 1 q infinity. Okay, and the terms is it can be rewritten as on the right hand side, the left hand side, that becomes only the terms containing denominator and numerator is 1 plus 1, that is 2 whole square, that is 4. So therefore summation from minus infinity to plus infinity, 4 divided by the last term, the denominator last term is here, that is 1 plus qn whole square into minus q to the power of n is equal to q infinity o to the power of 4 divided by minus q infinity o to the power of 4. So therefore, once again that value of 1 plus q to the power of n whole square, you can observe here, that can be written as in terms of positive integer, negative integer, and also if n is equal to 0, the terms can be written as 4 times summation n running from minus infinity to minus 1, the terms here, because we have to split the terms of width as n running from minus infinity to plus infinity. After that value of minus infinity to plus infinity, we can replace the value in the first series n by minus n. So therefore, it can be written as the terms is n running from 1 to infinity after the replacement of n by replacement of n by minus n. So therefore, that becomes n running from 1 to infinity after replacement of n by minus n. That negative integer can be written as n running from 1 to infinity minus q to the power of minus n divided by 1 plus q to the power of minus n whole square plus 1 by 4 times 1 by 4 plus summation n running from 1 to infinity. This one is positive integer minus q to the power of n divided by 1 plus q to the power of n whole square is equal to the last step definition, that is the terms is q infinity divided by minus q infinity, that is the statement of phi of minus q's definition, that is phi of minus q whole to the power of 4, because the power is 4 is there. And also here we have to take minus q to the power of n as a common term. It can be written as 1 plus q to the power of n. It will goes to numerator, that becomes minus q to the power of plus 2n. Here minus q to the power of n is there, that becomes q to the power of n. So therefore, that is minus q to the power of n. That retains that the first one and the second one values. So therefore, 4 times summation n running from 1 to infinity minus q to the power of n divided by 1 plus q to the power of n whole square plus 1 by 4 plus summation n running from 1 to infinity minus q to the power of n divided by 1 plus q to the power of n whole square is equal to phi to the power of 4 of minus cube. Okay, because that the first series we can observe here minus q to the power of n divided by 1 plus q to the power of minus n whole square, or it can be written as in the denominator we can take minus q to the power of n as a common term, that becomes minus q to the power of 2n into 1 plus q to the power of n square, because square term is there. We have to replace when I have to taking minus q to the power of n as a common term, that becomes square is then q to the power of minus 2n. It will goes to numerator, that is minus q to the power of n plus q to the power of 2n, that becomes q to the power of n, or it can be written as minus q to the power of n divided by 1 plus q to the power of n whole square. So, or it can be written as the terms is that 2 times this one is there, and also when I have to multiply the terms of 4 inside, it's a 4 plus 4, that is 8. Again when I have to, that is 4 by 4 is 1. So therefore, phi to the power of 4 of minus q is equal to 1 plus 8 times minus q to the power of n divided by 1 plus qn whole square. So when I have to replace q by minus q in the above equation, it can be written as it is a minus q is there, so minus into minus plus, it's a phi to the power of 4 of q is equal to 1 plus 8 times summation n running from 1 to infinity q to the power of n divided by 1 plus minus q to the power of n whole square. Okay, whole square, or phi to the power of 4 of q is equal to 1 plus 8 times summation n from 1 to infinity q to the power of n into 1 divided by 1 plus q to the power of n whole square. We know this statement, that is the terms of the very familiar formula, 1 divided by 1 minus q square can be written as the terms is 1 plus 2q plus 3q square plus 3x square plus 4x cube up to the terms is summation m running from 1 to infinity m times q to the power, x to the power of m minus 1. We can compare the terms of here x by the terms of minus q to the power of minus n. So therefore, x can observe here the difference of these two terms here, can observe this term with compare with this term. So therefore, this minus x is equal to q to the power of n whole square. Then what is the value of x? X can be written as minus, you can multiplying throughout by minus here, that is x is equal to minus of minus q to the power of minus n. So therefore, by using this one, so 1 divided by 1 plus minus qn whole square can be written as summation m running from 1 to infinity m times, we can observe terms of m times minus of minus q to the power of n, minus of minus q to the power of n whole to the power of m minus 1. So therefore, phi to the power of 4 of q is equal to 1 plus 8 times summation n running from 1 to infinity q to the power of n into summation m running from 1 to infinity m times minus of minus q whole to the power of n, that whole to the power of m minus n. Or the terms is, you can split this one as two terms, as minus 1 to the power of m minus 1 and here minus q to the power of m in n into m minus 1. So therefore, that is equal to 1 plus 8 times summation n running from 1 to infinity q to the power of n into summation m running from 1 to infinity m times minus 1 to the power of m minus 1 into minus q to the power of n into m minus 1, or that is a 1 plus 8 times summation m running from 1 to infinity m into minus 1 to the power of m minus 1. We have to multiply this one with q here. So that is q to the power of n into minus 1 to the power of n. We have to interchange the values, interchange that series. We are collecting the terms of m series, and also here the collecting of n with the terms of m is also here q to the power of n into minus 1 to the power of n into m minus 1 into q to the power of n into m minus 1. That is equal to, that is 1 plus 8 times, that is m series is unaltered as m running from 1 to infinity m into minus 1 to the power of m minus 1 into summation n running from 1 to infinity minus 1 to the power of n times m minus 1. So we have to multiply this term here, that is q to the power of n plus q to the power of mn minus m. Here plus n and minus n get cancelled, that becomes q to the power of mn. Therefore, it can be rewritten as phi to the power of 4 of q is equal to summation, that's equal to 1 plus 8 times summation m running from 1 to infinity m into minus 1 to the power of m minus 1 into the summation n running from 1 to infinity minus 1 to the power of m minus 1 whole to the power of n into qm whole to the power of n. Or it can be rewritten as the terms is here, both the terms is power is n is there, or it can be written as minus 1 to the power of mn in my m minus 1 into q to the power of n whole to the power of n. So therefore, that is 1 plus 8 times summation m running from 1 to infinity m into minus 1 to the power of m minus 1 into summation n running from 1 to infinity minus 1 to the power of m minus 1 into q to the power of m whole to the power of n. But we know the value of summation n running from 1 to infinity x to the power of n is equal to the well-known formula, that is equal to x plus x square plus x cube up, that is equal to x divided by 1 minus x, because the terms is not containing 0, that will goes to RHS side, that becomes x divided by x 1 minus x. So when I have to compare these two terms here, these two terms with this one, the formula, so that becomes when I should replace x divided by minus 1 to the power of m minus 1 into q to the power of m. So overall, that this series can be written as the series as, that is x divided by 1 minus x. What is x? X is minus 1 to the power of m minus 1 into x to the q to the power of m. So therefore, we have to substitute the terms. It is 1 plus 8 times summation m running from 1 to infinity m into minus 1 to the power of m minus 1. So we have to replace the value of this one is minus 1 to x divided by, what is x? X is minus 1 to the power of m minus 1 into q to the power of m, okay, that divided by 1 minus x, that is 1 minus of minus 1 to the power of m minus 1 into q to the power of n. Here minus 1 to the power of minus 1, you can split on minus 1 to the power of m, or it can be rewritten as here also minus 1 to the power of m minus 1, here also minus 1 to the power of m minus 1, that becomes 2 minus 1 to the power of 2 times m minus 1. So that is 1 plus 8 times summation m running from 1 to infinity m times minus 1 to the power of 2 times m minus 1, that is minus 1 to the power of 2 means that is equal to 1 into minus 1 means that is this value becomes 1 into q to the power of m divided by 1 minus of, we split this one, minus 1 to the power of minus 1 minus 1 to the power of m. So here minus 1 to the power minus 1 whole to the power of minus 1 means that is minus 1. So minus into minus, that becomes plus. Here minus q to the power of m into q to the power of m, or it can be written as phi to the power of 4 of q is equal to 1 plus 8 times summation m running from 1 to infinity, here m into q to the power of m divided by 1 plus minus 1 to the power of m into q to the power of m. So again the terms is here, if m is even and if m is odd, this phi to the power of 4 of q is equal to 1 plus 8 times, if m is a odd, that is m running from 1 to infinity q to the 2 m by m is odd means that is 2m minus 1 into q to the power of 2m minus 1 divided by 1 minus q to the power of 2m minus 1. If m is even, that is summation m running from 1 to infinity 2m, we should replace m by 2m to the power of 2m divided by 1 plus, here minus 1 to the power of 2m, that becomes plus, here minus 1 to the power of 2m minus 1 means that is negative. So 1 plus q to the power of 2m. So therefore it can be rewritten as, here we have to, in this step we have to add and multiply the terms of summation. We can observe here, we can add and multiply, add and subtract the terms of summation m running from 1 to infinity 2m into q to the power of 2m divided by 1 minus q to the power of 2m. So we can add and subtract the terms of m running from 1 to infinity 2m into q to the power of 2m divided by 1 minus q to the power of 2m. So and also we can club the terms here. Here you can observe here, that is the terms is containing both even and odd term. Here this one is odd term and this one is even term. So overall the terms is that is m running from 1 to infinity. But here that we can observe the terms of 2m is a common term, q to the power of 2m is a common term. Here a minus b into a plus b term. So it can be rewritten as the terms is, and also we can take in that LCM. The next step, so these two terms are even and odd terms. So first two terms are even and odd terms. You can observe here. Okay, so that becomes, when I have to add the terms, that becomes m term, that is equal to 1 plus 8 times summation m running from 1 to infinity m into q to the power of m divided by 1 plus q to the power of m. Here we can take minus as a common term, and also what is the common term is q to the 2m into q to the power of m, and we can take in that LCM, that is 1 divided by q 1 minus q to the power of 2m into 1 divided by 1 plus q to the power of 2m. We can take in the cross multiplication, plus 1 and minus 1 get cancelled. We can after taking the LCM, the terms is here minus into minus, that is a plus q to the power of 2m, q to the power of 2m, that is 2 times q to the power of 2m. So here a minus b into a plus b terms there, 1 minus q to the power of 4m, that is we have to take 1 square minus q to the power of 2m whole square. So therefore it can be written as the terms is 1 plus 8 times summation m running from 1 to infinity m into q to the power of m divided by 1 plus q to the power of m minus summation m running from 1 to infinity 2m is already there, q to the power of 2m is already there. Again this one we have to cancel the terms is plus 1 and minus 1, that is 2 into 2 q to the power of 2m, that is 2 times here, that is 4m into q to the power of 2m into 2m plus 2m, that is also 4m. 1 minus q to the power of 2m whole square means that is q to the power of 4m. So therefore phi to the power of 4 of q is equal to 1 plus 8 times summation m running from 1 to infinity m into q to the power of m divided by 1 plus q to the power of m minus summation m running from 1 to infinity 4m times q to the power of 4m divided by 1 minus q to the power of 4m. That means the terms here the terms containing m, we have to subtract with the 4 terms. Okay, we can subtract the multiple of 4 terms by full term, we get phi to the power of 4 of q is equal to 1 plus 8 times summation m running from 1 to infinity m into q to the power of m divided by, this one is not plus, this one is a minus term, not the terms is minus, not plus, typing error, minus, and that is summation m running from 1 to infinity, the terms not containing 4 divides m, because we have to subtract here the terms, that is m into q to the power of m divided by 1 minus q to the power of m. And also the terms here phi to the power of 4 of q is equal to 1 plus 8 times summation m running from 1 to infinity, 4 does not divides m, that is m into q to the power of m divided by 1 minus q to the power of m. We know the terms of x divided by 1 minus x, that can be written as summation r running from 1 to infinity x to the power of r. Again, so again we are using this formula, we can replace what is x, x divided by, instead of the terms of q to the power of m, so it can be written as q to the power of m divided by 1 plus 1 minus q to the power of m is summation r running from 1 to infinity q to the power of m whole to the power of r. So therefore phi to the power of 4 of q is equal to 1 plus 8 times summation m running from 1 to infinity, 4 does not divide m into, can observe terms of m into r running from 1 to infinity q to the power of m whole to the power of r, or it can be written as phi to the power of 4 of q is equal to 1 plus 8 times summation m running from 1 to infinity, 4 does not divide m, but the terms is into r running from 1 to infinity, we have to multiply inside m into q to the power of mr. I have to take, put mr is equal to n, put mr is equal to n, then the values of what is mr is equal to m is, the terms is what is the value of m is, by using this one, what is the value of m, the terms is m is n by r. Okay, it can be rewritten as, the terms is phi to the power of 4 of q is equal to 1 plus 8 times summation m running from 1 to infinity, 4 does not divide m, r running from 1 to infinity n by r into q to the power of n. The terms is, you can take in the substitution, the terms is q to the power of n. Okay, and the terms is phi to the power of 4 of q is equal to 1 plus 8 times, the terms becomes r running from 1 to infinity, we have to interchange that series, d divides n, d divides n not infinity, the terms of 4 does not divides m, d into q to the power of n. You can observe the terms of d into q to the power of n. By using that, you can compare that this one as equation 2. You can observe terms of this one as equation 2, d divides n, the terms is, by employing equation 1 and 2, we get the terms is what is phi to the power of 4 of q is, that is 1 plus, by using that equation 1, that 1 plus summation m running from 1 to infinity r suffix 4 of n into q to the power of n is equal to, that is by using equation 2, that is equal to 1 plus 8 times summation r running from 1 to infinity d, that is a divisor, sum d divides n, 4 does not divide m, the terms of d into q to the power of m. So there is not n, the terms of not m, that is a n, typing error, that is a not 4 does not divides n. So we want to compare the coefficient of q to the power of n. Here n get 1 get cancelled. One also we can compare the q to the power of n. Okay, the terms containing here also one n running from 1 to infinity, here r running from 1 to infinity. So the terms is, so it can be written as r suffix 4 of n is equal to 8 times summation d divides n, 4 does not divide n, the divisor sum. So that is the end of the 4 square theorem. The next one theorem, the number of partition of n in which no parts repeated more than k minus 1 time. Can observe that statement. The number of partition of n in which no parts is repeated more than k minus 1 times is equal to the number of partition of n which is no part divisible by k. Okay, the first statement, proof, the number of partition of n in which no parts is required more than k minus 1 times. Okay, not k minus 1 time. So that is equal to, okay, that is equal to 1 plus q to the power of 1 plus 1 plus q to the power of 1 plus 1 plus q to the power of 1 plus 1 plus 1 up to, observe the terms is k minus 1 times. No parts is required more than k minus 1 times. So 1 plus how many terms? That is k minus 1 times. Similarly, into 1 plus q square q to the power of 2 plus 2 plus q to the power of 2 plus 2 up to q to the power of 2 plus 2 plus 2 up to the terms of k minus 1 times. Similarly, in terms of into 1 plus q cube plus 1 plus plus q to the power of 3 plus 3 q to the power of 3 plus 3 plus 3 up to q to the power of 3 plus 3 plus 3 up to k minus 1 times. So therefore, it can be written as that is representation is 1 plus q square plus q up to k minus 1 times. Next, again 1 plus q square plus q to the power of 4 up to the terms is q to the power of 2 into k minus 1. Again multiple of 3, that is 1 plus q cube plus q to the power of 6 up to q to the power of 3 into k minus 1. You know this one statement, the terms of that is a 1 divided by the first one 1 plus q square plus q up to q to the power of k minus 1 is, that is in terms of GP, that is 1 minus q to the power of k divided by 1 minus q, because we know the formula, that is 1 plus r square plus up to r to the power of n minus 1 is equal to 1 minus r to the power of n divided by 1 by r. So using this statement, the terms can be written as this. The first one can be written as 1 minus k to the power q to the power of k divided by 1 minus q. The second one is 1 minus q to the power of 2k divided by 1 minus k, and the next one is 1 minus q to the power of 3k divided by 1 minus k. So therefore this one, the terms is, okay, replace that values, and so we have to write by using q shifted factorial. The first term is my q to the power of k, and the jumping term or shifted term is q to the power of k. So therefore that is the numerator term is q to the power of k infinity, and the denominator term is q square q cube. So therefore we can easily predict the terms of by using q shifted factorial, that is a q infinity. So overall the terms is q to the power of k infinity divided by q infinity. So or we can express the terms of the numerator denominator, that is q infinity, can be written as qk infinity q square qk infinity q cube qk infinity up to the terms of q to the power of k minus 1 qk infinity into qk infinity. So we can cancel the terms of both numerator and denominator containing qk infinity. The remaining term is 1 divided by qk infinity, q square qk infinity, q cube qk infinity up to the terms of q to the power of k minus 1 qk infinity. The terms is, it can be written as the terms of q to the power of k, the 1 divided by the terms is, you can observe the term here is the terms containing k, k and q square, q cube q to the power of k. Again, by using q shifted factorial, it can be written as the term is, you can observe the terms here, that is q suffix k minus 1 times. You can observe terms of, that is by using the terms here, that is q k minus 1. Okay, so this one means the number of partition of n in which, you can observe terms of the number of partition of n in which no part is divisible by k. You can observe terms of, because it is not containing the in terms of a power of k, this is k minus 1 up to k minus 1, not in terms of k. So therefore this one can be written as the number of partition of n in which no part is divisible by k. For example, we can take that counter example. If n is equal to 6, then the partition of 6 is 6, 5 plus 1, 4, 4 plus 1 plus 1, 3 plus 3, 3 plus 2 plus 1, 3 plus 1 plus 1 plus 1, again 2 plus 2 plus 2, 2 plus 2 plus 1 plus 1, 2 plus 1 plus 1 plus 1, and the remainings are 1 plus 1 plus 1 up to 6, the values. So we have to restrict the terms if k is equal to 3 and let a be the number of partition of n in which no part is repeated more than k minus 1 times. K minus 1 means here k is 3, no part is more than 2 times. You can observe terms of no part is more than 2 times. So then what is the definition of a? A is not more than 2 times. You can observe terms of number of parts is not more than 2 times. Here a is equal to 6 and the next one is 5 plus 1, the next one is 4 plus 1 plus 1, again the terms of 4 plus 2. Okay, the terms is next one is 4 plus, here missing the terms of 4 plus 2. Okay, here 4 plus 1 plus 1, again 3 plus 3, again 3 plus 2 plus 1. Here the terms is containing 1 is more than 2 times, won't take this one. Here also 2 plus 2 plus 2, because the terms is not more than 2 times, won't take this values. Here also 2 plus 2 plus 1 plus 1 you can take, but here 1 plus 1 plus 1 plus 1, here also 1 plus 1 plus 1, that is not more than 2 times. Okay, any parts is not more than 2 times, so therefore a is equal to 7. The cardinality of a is equal to 7. What is the condition of b? Let b be the number of partition of n, that is n is equal to 6, in which no part is divisible by k, that is k is equal to 3. So that is the terms of not divisible by 3. What is b is equal to? Here 6 is there, it is divisible by 6, we won't take. Next one is 5 plus 1, we can take. Again next one is 4 plus 2, we can take, because it's not divisible by 3 of any part. That is here 4 plus 1 plus 1, here 3 is there, you won't take that part. This one is also won't take, and 3 is there here, and next term is this 2 plus 2 plus 2, again 2 plus 1 plus 1 plus 1, again the remaining terms of 2 plus 1 plus 1 plus 1 and 2 plus 1 plus 1. So therefore the cardinality of b is equal also 7 terms. Suppose to take if n is equal to 6, the same condition. Okay, you have to restrict the k is equal to 2, that means k minus 1 times means that is 2 minus 1, that's equal to 1 times. So therefore not more than 1 times, no repeated terms, that is a is equal to 6, 5 plus 1, again the terms of 3 plus 2 plus 1. The remaining are repeated terms. So therefore, the cardinality of A is equal to 4. Similarly, when I have to take B, it is not divisible by 2. So it is not divisible by 2 means we won't take 6. That is next term is 5. 5 plus 1. Again 4 is divisible by 2. We won't take, and 3 plus 3. Here the terms is 3 plus 1 plus 1. Again the last number is 1 plus 1. So therefore the cardinality of B is equal to 4. So hence the theorem is holds good. Okay, in this we are ending the session. Thank you.